Hello everyone, and welcome back to my course on discrete mathematics. And in this online lecture today, we are going to deal with the topics on relations. As we have already dealt with functions, and here in relations we are going to see how different sets can be related to one another. So what is the relation in general? Let A and B be sets, and a binary relation R is a subset of A and B. Let's see some example here. Let A be the students in the CS major, and say Alice, Bob, Claire, Dan. They are the students, and B be the courses that department offers, like CS 101, CS 201, CS 202. Let B be this set. And now we are going to have a relationship between these two sets. We specify the relation R is A and B as a set that lists all students where A is an element of A enrolled in the class and B is an element of B. So we can state it in another way, where we have the relation where Alice, CS 101, Bob, CS 201, Bob, CS 202, Dan, CS 201, Dan, CS 202. So as you can see, Alice, Bob, Dan, they are related to the other set which has the course. In other words, Alice is taking the course CS 101. Let's put it another way, how to represent the same relationship. Let A be the cities in US and B be the states in US. Let R means we are establishing this relationship. A in city, A is a city in state B. Let's say, for example, you have Philadelphia and Portland, for example. You have Portland and Oregon, and these are the relationship that you are developing between these two sections. If you are more familiar with other cities, you can also come up with these. For example, you can think of other places where you can also use based on your relationship that you have. Whether it's about these cities and states, or it about, in other words, you can also come up with some other terms that you can use. Let's talk about some representation, how it can be done. Like, for example, Alice is taking the course CS 101, so they have a relationship, Alice and the course. Bob is taking two courses, CS 201 and CS 202. Likewise, Dan is as well. So you can clearly see that Alice, Bob, Dan, they are taking courses, but Claire is not taking a course, which means that this kind of relationship is not really a function, but it is a valid relation. So as you can see here, this table also represents the same idea of Alice, Bob, Dan taking the course, though Claire is not in this list. Let's briefly summarize the relationship between, or the comparison of relations and functions. Not all relations are functions, but consider the following case in which you have a function which is a relation, and all functions are relations. Yes, not all relations are functions. As in the previous case, we saw that here this in fact is a relationship that shows between the two sets of students as well as the classes they are taking in the CS department, but it doesn't represent a function. Whereas here, as we can see, this is a function, and of course it's a relationship. It is a relation. So not all relations are functions, but all functions are relations. So that's one thing to note. So like we have this question, when to use which one, either functions or relations. We talked about functions. We know what is a function, what is the inverse function, and so on. So a function is used when we need to obtain a single result from any element in a domain. A function is used when you need a single result for any element in the domain. Let's consider, like, you have sine, cosine, tangent. These are some of the functions in which we are expecting one single result. Relation is when there are multiple mapping between domain and codomain. Yeah, we saw multiple mapping. For example, student enrolled in multiple courses. Yeah, that is possible in case of a relation. Relation on a set. A relation on set A is a relation from A to A. In other words, domain and codomain are the same set in this case. So we will generally be studying the relation of this type in which we have the sets. So we have set A, which is 1, 2, 3, 4, and we which have ordered pair in the relation R equals A comma B, where we say A divides B. So we are developing a relation like 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 2 comma 2, 2 comma 4, 2 comma 3, 3 comma 3, 4 comma 4. So as we develop this relation, we can see that we have ordered pair of pairs. We have developed ordered pairs in which you have 1 is related to all things, and 2 is related to 2 and 4, because 2 you can divide by 2, as well as 4 can also be divided. So 3 is related to 3, 4 is related to 4. So this is this relation, the whole relationship established by means of this thing, A divides B. Yes, 2 divides 4, 2 divides 2. So 2 is connected to both 2 and 4. 3 divides 3. Yes, so 3 is connected to 3. 4 divides 4. So 4 is connected to 4. Or in other words, they are related. In other words, 1 divides 4, 3, 2, 1. So they are connected. In other words, the relationship here that is been established in itself brings out an ordered pair. It brings out an ordered pair. So A divides B. So this is for, you have 1, 2, 3, and 4. So this kind of relationship has been established because of this particular conditions. We have A divides B for the given set 1, 2, 3, 4, and we are developing this ordered pair. So in other words, here is another way of looking at this relationship or relation of this ordered pair. Let's see about some properties. There are 6 properties of relations that we are going to study. First is reflexive. Second one is irreflexive. Third one is symmetric. Fourth one is asymmetric. Fifth one is antisymmetric. The last one is transitive. Let's go one by one and see what is the properties of these relations. First one is reflectivity or reflexivity. What is it? A relation is reflexive if every element is related to itself. Every element is related to itself, then we call it as reflective. You can think about how a mirror is reflecting yourself. Well, you have A comma A is an element of the relation, or let's see an example of this relation. So A is equal to A, some kind of statement. So you have equal to sign, less than or equal to sign, greater than or equal to sign. These represents this reflexive relation. As we study about reflexive relation, let's also think about what is not reflexive. So example of not reflexive will be like greater than, less than. Let's talk about what is irreflexivity. Generally, a relation is irreflexive if every element is not related to itself. It's just kind of opposite, right? So we have A, comma A is not related to R. In other words, the opposite of reflexivity, that's what we talk about. And here the relationship has been established by means of the signs like less than or greater than. Again, the opposite of this would be equal to, less than or equal to, greater than or equal to. Let's move on and see, compare these two different things, reflexive and irreflexive, or reflexivity and irreflectivity. A relation can be neither reflexive nor irreflexive if you have some elements are related to themselves, others are not. Yeah, there may be some cases in which you have this condition. So we will see this example later on when we talk about other properties. Now let's switch to the symmetry. What is a symmetry? A relation is symmetry if for every A, comma B is an element of R, then B, comma A is also an element of R. Yes, you see a symmetry between these two things, A and B, B and A. Let's see how this can be established. So you have this equal to sign is an example where we can bring out this symmetric relationship. We won't talk about this twin of functions. Let's skip it off and let's see examples of relations that are not symmetric, like less than, greater than, less than or equal to, greater than or equal to. They are not symmetric. Now let's look at what is asymmetry. A relation is asymmetric if for every A, comma B, which is an element of R, then B, comma A is not an element of R. Looks like almost just the opposite of symmetry. Exactly. So which means that the relationship that we are going to talk about here is less than, greater than, and the opposite of this, like non-asymmetric, would be equal to, yes, or less than or equal to, greater than or equal to, and so on. Okay, since we have talked about symmetric and asymmetric, now next is quite interesting part, which is antisymmetry. What is the difference then? What is an antisymmetry? A relationship is antisymmetric if for every A, comma B is an element of R, then B, comma A is also an element of R is true only when A equals B. That's an interesting observation, an interesting relationship that we talk about. The relation develops. Antisymmetry is not opposite of symmetry, and it's also not that as equal to that of asymmetric. So we can see it has its own relation. So you can establish this by means of equal to, less than or equal to, greater than or equal to, and that are relations that are not antisymmetric is less than or equal to, greater than or equal to. Yeah. So there are a few notes on symmetric relations we can think of. A relation can be neither symmetric or asymmetric. When we say A, comma B, given that A equals the absolute value of B. So this is not symmetric. So minus 4 is not related to itself, for example. Yeah. So that's why specifically in this example we have this absolute sign. When you have absolute, you know that the minus is negated. So this is not an asymmetric either. So 4 is related to itself. So note that it is an antisymmetric, in which we say that there is a condition, right, in which we say A and B, they should be equal. Okay, coming to this transitivity, is a similar principle that we have seen earlier since we talked about this Boolean relationship. So a relation is transitive if for every A comma B is an element of R and B comma C is an element of R, then A comma C is an element of R. So if A is less than B and B is less than C, then A is less than C. So that's the relationship that we talk about in transitivity. So thus you have less than is transitive, and you can see if A is equal to B, B equal to C, and A equal to C. So we can see the relations. That's transitivity. When A is equal to B and B is equal to C, therefore A is equal to C, or then A is equal to C. So that's the transitivity. So you have equal to sign as well. So there are a few more relations that we have in case of transitivity. Let's see this example here. Consider is ancestor of function is given, and let Alice be Bob's parent and Bob be Claire's parent. Thus Alice is an ancestor of Bob and Bob is an ancestor of Claire. So we have this relation, thus Alice is ancestor of Claire. So this is the conclusion in which we can say that is ancestor of function is transitive relation, because they establishes the parent child relation. We know Alice is Bob's parent and Bob is Claire's parent. Therefore Alice is ancestor of Claire. So if parents of function, let's say Alice is Bob's parent, Bob is Claire's parent. So Alice is parent of Bob and Bob is parent of Claire. Therefore Alice is not a parent of Claire. Alice is ancestor but not a parent, apparently, yeah. So that's, therefore this function is parent of is not a transitive relation. So relations of relations, let's summarize it in general. These are some of the symbols that are used to represent these different relations: equal to, less than, greater than or equal to, less than or equal to. These things can be used to represent various relations, these 6 different relations that we just talked about. Combining relations, there are 2 ways to combine relations, R1 and R2. You can either use Boolean operators to combine it, or you can use composition. So let's do via Boolean operators. For example, we have 2 relations, R that is greater than equal to or R less than equal to. Let's see that this you have this union operator, or greater than or equal to union or less than or equal to. So you can represent that all numbers can be stated as just using union operation. So you can use OR operator. Yeah, equivalent Boolean operation is OR, greater than or equal to or less than or equal to. And again, when you use intersection of these 2 relations, then you can use AND as a Boolean operator, greater than and less than or equal to. So again, you are using exclusive OR. So you use OR but not both. And here the number greater than that are not also less than. So you have used the not operation. And again, here less than. Previously we have used that greater than, that are not also less than. Now you are using less than, that are all not, also not greater than. So they are strictly less than. So we have created a possible results with this empty set. So these are some of the relations we developed via Boolean operator. Let's talk about the relational composition. So let R be a relation of A and B, and S be a relation of B to C. So A is an element of A, B is an element of B, C is an element of C. Then you have A comma B is an element of R, and P comma C is an element of S. So let's try to have this relations coming up. Then we have the composite of R and S consist of the ordered pair A comma C. So we denote the relation S composite R, or it's kind of S dot R that comes there. So note that it comes first while writing this composition part. So we are combining the relation R and S via relational composition here. So as we do that, let M be the relation is mother of, F be the relation is father of, and here we have the composition of M and F composite function. So if A comma B is element of F, then A is the father of B. That is how you develop this composition relation. And if B comma C is an element of M, then B is the mother of C. So thus M composition of F denotes the relation maternal grandfather. Well, let's talk about the next part, the reverse way. What is F composite of M? So if A comma B is an element of M, then we say that A is the mother of B, and if B comma C is the element of F, then we say B is the father of F. So in this case, what happens to F composite of M? So this denotes the relation parental grandmother. Here is another relation, M composite of M. If A comma B is an element of M, then A is the mother of B, and if A comma B comma C is the element of M, then B is the mother of C. So now we are establishing the relation M composite of M denotes the relation maternal grandmother, both or M in any way. So note that M and F are not transitive relation. Yeah, they are not bringing up a transitive relation. When we use this relational composition, it can bring other relations that we have just seen. So given R, and R composite of R can be denoted by R square, and R square composite of R can be written as R cube. So when I say M power 3, we could say like your mother's mother's mother. Yeah, you can think of other examples as well. Let's now review some matrix form in which we can represent various relations. We will be only dealing with 0 and 1 matrices. So let's the element of the matrix of 0 or 1. Here is one example of this matrix. The matrix used for Boolean operations. Let's say 1 represents true and 0 represents false. Here you have this transposition. So given a matrix M, the transposition of M denotes M transpose if matrix obtained by switching the columns and rows of M. So here is an example. We have 1, 2, 3, 4, 5, 6. 1, 2, 3 is the first row, and the second row is 4, 5, 6. And the transpose of this matrix becomes 1, 2, 3, that becomes the column. First column, the second column becomes 4, 5, 6. So that's the transposition here. So we have an example of a bigger matrix here, just the same idea, same principle we are using to transpose this matrix. Let's see how we are going to use that later on. And usually we go for this kind of transpose matrix, we use square matrix so that the diagonal remained unchanged, as you can see here. Let's say matrix joins. A join of two matrices performs Boolean operation OR on each relative entries of the matrix. So matrix must be of same size if you want to do this joining of this matrix. And if you are using OR, we can represent the same logical symbol that we used, similar to V. And here is an example of how you are going to combine these two. And this is basically OR operation you do, because we already told that 1 represent 2 and 0 represent false, and that's a Boolean relationship, and the whole matrix can be simply written. So as you can see from this example, it's just the OR operation has been performed, and finally you have this whole matrix as the output. Let's go further and meet more about this matrix. A meet of two matrices perform a Boolean AND on each relative entries of the matrix. Let's see an example here. So we just use, for AND operation, we use, it's kind of a cap or a kind of symbol is been used, and the same logic has been used for performing this task, and you can see here the AND operation is performed, right? So only, for example, here 1 and 1 is 1, for example. Just for your verification, I'm just giving this example. Let's move on and see the Boolean product here. A Boolean product of two matrices is similar to matrix multiplication, exactly. So we talk about this form C11. The first column and first row, you have this A11 times B11 plus A12 times B21 plus A13 times B31 plus A14 times B41. So instead of sum of product, it's conjunction and of disjunctions, ands and ors we use. So A11 is, or C11 is A11 and B11, or A12 and B21, or A13 and B31, or A14 and B41. Could you see the relationship? Whenever there is a multiplication, we use AND operation, and whenever there is an addition, we use a OR operator. So based on that, we can simply bring out this relationship. So if you want to find this one, which is supposed to be C11, so you know what is the relationship that you are going to come up with. So you can use this two-part row and column of the previous matrices that are used for product. So you can use this to evaluate the result one by one. You go from A11 and B11, then you go A12, B21, then you go A13, B31, A14 and B41. So using these operations, you can perform this, and likewise you can fill in the whole matrices. That's the product of this Boolean matrix. Let's talk about relationship establishing using matrices. List of element of set A and B in particular order. So the order doesn't matter, but we generally use the ascending order. Let's create this matrix MR with Mij, and its Mij is 1 if A comma B is an element of R, and it's 0 when it's not an element of R. Using this relation, let's consider who enrolled in this class. Like, Alice, Bob, Claire and Dan are the part of set A, and the set B is CS 101, 201, 202. So in relations, a person is enrolled in the class. If he is enrolled, then we have a relation. So based on that, let's establish this matrix. So we have a table here, and based on this table, you're putting up this matrices. So this matrix is actually giving up the relationship between the two sets that we have, and one represents there is a relation. Let's go further. What is the use and how computer view these relations. this kind of a two-dimensional array is how it's been viewed, and it's very easy to view relationship properties when we have, generally we consider relations on single sets. In other words, the domain and codomain are of the same set, and we usually use the matrix of square type. Let's talk about this reflective relations. Reflexivity, we know that relation is less than or equal to, and on which every element is related to itself. And you can also use other properties. Let's start with this one, and for matrices less than or equal to, we are establishing this element of matrix with zeros and ones. Let's say here the diagonal element is all 1, and that is an indication that this has a reflexive relation. If the center main diagonals are all 1s, the relation is reflexive. Irreflexive, less than or equal to. For example, we are taking this, and we are again we know that one which every element is not related to itself. Let's try to see this matrix. Here again, look at the diagonal elements. Here you have all zeros, so just the opposite of reflexive, so we call it as irreflexive. Symmetry, so one which if A is related to B, then B is related to A. So how can we establish this relation in a matrix form? So you can think about this elements on each of those triangles, upper and the lower triangle. So if for every value it is equal to the value that is its transpose position, then you are trying to get the relationship there. Asymmetry, consider asymmetric relations like maybe less than. Here, if one element, or if A is related to B and B is not related to A, we call it as asymmetry. So let's see the same relations. So here all those in the upper triangle and lower triangle are not related, because the upper triangle has 1s and the lower triangle has zeros. For every values and the values and in its transpose position, if they are not both 1, then relation is asymmetry. Yes, asymmetric relation also must be irreflexive. That's one hint that we have. Thus the main diagonals here we have zeros because of irreflexive. Yeah, you can think back about that relations as well. Antisymmetry, if for every value and the value in its transposed position, if they are not both 1, then relationship is antisymmetry. The center diagonal can have both 1 and zeros. So let's see here. Let's take this relation less than or equal to. So one which if A is related to B and B is not related to A unless A is equal to B. So that's the condition, unless A equal to B. So this gives us an example. So the center can be either 1 and 0, but the upper and lower triangles are completely opposite to one another. So upper part is 1s and lower part is 0, and the center part, as we said, it can be either 1 or 0, or it can have both 1s and 0s. Transitivity, well, we can use less than or equal to relations here, and if A is related to B and B is related to C, then we say A is related to C. That is the idea. So let's say here with the upper triangle we have 1s there. If for every spot A comma B and B comma C that each have 1, there is 1 at A comma C. So that's the relation here. We have the first part. Let's say this is A comma B and this is B comma C. The last one is A comma C. So they are all equal. So when they are equal, we can say that they have this transitivity property. So usually the matrix doesn't show this property easily, so it's not easy for us to get this property right away. But as far as other properties are concerned, it's quite easy for us to determine right away. Let's combining the Boolean relations, Boolean properties and relations. Let's say MR, which is the matrix given, and MS is another matrix given to us. Let's say you are taking the OR of these two matrices. You are ORing these two matrices, Boolean OR. So you have come up with another new matrix after taking the OR, and you are having the AND function. So joining or join is OR, meet is AND, and then you can see taking the same as this other function here. We are coming up with new different functions of case by case. So with these cases, let's see one after another. For example, how this has been established. We have seen earlier like actual matrix form that we talked about in the earlier slides to come up with C11 as well. So based on this rows and columns of the given matrix, we can calculate every element of the new matrix here. Yes, based on this we are calculating the new element. The same idea that we have used in the past to calculate. Representing relations using directed graphs. A directed graph can be used to represent the relations. So a set V is the matrix or vertices or the nodes of the given graph. E is the edge of the graph, and if A comma B is in relation, then there is an arrow of A to B. So we generally use the relation in a single set. Let's say relations A comma B, where A divides B. Here is an example. We talked about it in the past, how 1 divides 1, 2, 3, 4, 2 divides 2, 1, 4, 3 divides 3, 4 divides 2. So this is how we did in the past to establish a relations. Now let's say how we can do that using the graph. Here it is. So 1 is connected to all things. 1 divides 1, 1 divides 2, 3, 4. And 2 is connected to itself. 2 divides 4, 2 divides itself, and 2 divides 4, and 4 divides itself, 3 divides itself. So this is the new relationship that we are establishing using the graph. Reflexive relations, let's say how it can be done. Less than or equal to one which element or one which every element is related to itself, we call reflexive. So here is the set A is given as 1, 2, 3, 4, 5, and you are having this loop, and they are all related to itself. 1 is related to itself, 2 is related to itself, 3 is related to itself, 4 is related to itself, 5 is related to itself. If every node has a loop, a relationship is reflective. So yeah, whenever there is a loop, you can call it as reflexive. So you have a loop here. That's what I'm talking about. Everything has a loop. So this establishes the reflexive relation. Irreflexive, less than or equal to, on which every element is not related to itself. So you can expect that there is no loop, then it is irreflexive. If every node does not have a loop, it is irreflexive. Symmetry, you can see if A is related to B and B is related to A for all values of A and B. So when you have an arrow from say 1 to 3, then you should have another arrow from 3 to 1. Or in other words, when you have an arrow from 1 to 4, then you have an arrow from 4 to 1. So if A is related to B, then B is related to A. That's what we talk about. If 1 is related to 5, then 5 is related to 1. So if for every edge there is an edge in other directions, so these arrows we call it as edge, then the relation is symmetric. Loops are allowed and do not need edges in other direction. Yes, we have loops that has been allowed here. So this relation is neither reflexive or irreflexive. So we can think about that as well. So here is one. This is called anti-parallel pairs. That's why we have this relation. Asymmetric, less than or equal to, or just symbol is less than. If A is related to B and B is not related to A for all A and B. So we can see that's kind of opposite. So this is an example where A is related to B, but 1 is related to 2, but 2 is not related to 1. You have an edge from 1 to 2, but there is no edge back from 2 to 1. A digraph is asymmetric if for every edge there is not an edge in other direction, then relation is asymmetric. And loops are not allowed in asymmetric digraphs. That's one point. But you can call this is very similar to irreflexive. Yeah, they have the same property. Antisymmetry, less than or equal to. If A is related to B and B is not related to A unless A is equal to B. So let's say here, if A is related to, if 1 is related to 2, then 2 is not related to 1, unless 1 is equal to 2. So that kind of relationship. If for every edge there is not an edge in other direction, then the relation is antisymmetric. So loops are allowed in this diagram of antisymmetry. Transitivity, if A is related to B and B is related to C, then A is related to C. Less than or equal to, we can try this one. So if A is related to, if 1 is related to 2 and 2 is related to 3, then 1 is related to 3. So we have we have an edge or arrow from 1 to 2, and then we have one from 2 to 3. Therefore we also have another from 1 to 3. So that's how it is. We have one arrow here, that is 1 to 2, then we have one here, this is 2 to 3, therefore we have another one here, 1 to 3. That's transitivity. A digraph is transitivity if for there is an edge from A to C when there is an edge from A to B and B to C. Application of digraph, we can see this kind of map as an example. This is a city map, and from the aerial view, and you have roads there and junctions. So you can just remove the unwanted things. Now you just have these whole map with the roads and all the junctions being placed with the yellow dot. And you can see there is a loop also given, the backwards, if not every road has that, but some parts. So you can remove, still you can remove unwanted things. So now just you have this whole graph of this simple part of the city that has been directed. Now we can traverse and see which part is having the transitivity property or reflective property. For example, you can see here, now you have a loop for all the nodes that is being given. And we can establish different relationship of this particular area of the city. Say you are trying to traverse from this point, start point and end point, you can see there is one way, this way of going to that place that is indicated in red color, and this is quite straightforward route, right? Yeah, and this is not symmetric relation. You can think of different relationship that it can provide us. Say if you're taking another route, say there's another route given here, the red, and this route has another property. Think of that. Yes, it's a symmetric property, right? All things has a backward path as well, so that is symmetric. So likewise, you can think of different properties. So here's a sample questions for which you can think of the different relationship that these given graph has. That's for your examination. You can think about it. You can think about what is the relationship these graphs represent. Think for a moment as an exercise for you. So here's one example that I have come up with for this problems, the question that I have here is how many symmetric relations are there on a set with n elements. It's kind of a proof, a theorem. So let's briefly see what it is. Consider a matrix symmetric relation R on a set with n elements. Then it's given to be in a form of a matrix. We don't know how many columns and rows. The center diagonals can have any values, so it can have 0 or 1. And then the upper triangle is determined. Once the upper triangle is determined, the lower triangle must be transposed, just the opposite of the upper triangle. It has the transpose values. How many ways there are to fill the center diagonals and the upper triangle is another question. There are n square elements in the matrix, so there are n elements in the center diagonal, and thus 2 power n ways to fill zeros and ones in this diagonal part. Thus you have n square minus n by 2 elements in each triangle. That's upper and lower triangle. Thus you have 2 power n square minus n by 2 ways to fill zeros and ones in the triangle. So there are different ways, so you can look at these answers. We are not going to prove it. I have just given this as an example for you to check how many symmetric relations are there in a set with n elements. We are not restricting any numbers, but n elements. So this is a simple way for us to understand this relations, how they are represented using this matrix. We are not proving it anyway. So this is for your reference. And we have seen many parts today, especially about relationship and how the relations of two different sets can be established, and there are different properties that we examined. And there are a lot more about relation to come, and we'll stop here for today's lecture, and when we come back we discuss more on the relations. So until then, have a good time. Goodbye then.